Hi, my name is Alan. I am a final year electrical engineering student studying at Monash University. My project is about developing robust algorithms to estimate blood pressure using the data from wearable sensors. Heart disease is currently a leading cause of death in most of the developed countries. One of the most effective and convenient way to track heart condition is by monitoring blood pressure. However, current cuff-based technology has many limitations. Patients cannot move during blood pressure measurement, and each measurement is going to take a few minutes. It's much more ideal to have continuous blood pressure monitoring. The aim of the project is to develop robust algorithms to estimate blood pressure using the data from wearable sensors. In this project, we use PPG sensor and ECG sensor. In the end of the project, the algorithms must be able to continuously estimate blood pressure, which is a significant improvement from traditional cuff technology. Wearable devices usually have higher noise level and lower signal-noise ratio. Therefore, the algorithm must be able to tolerate high noise level so that it can be applied in wearable device application. Ideally, the algorithm should be able to provide accurate blood pressure estimation during motion. This is currently not available among commercial products because signals are significantly corrupted during motion. However, in the end of this project, this has been successfully done. Moreover, this algorithm should have low requirement of hardware just to make it more challenging. Firstly, let me introduce how data collection is done. In order to successfully calibrate the algorithms, signals must be recorded when patient has different blood pressure value. The data was taken when the patient was lying, from lying to sitting, and from sitting to standing. All these different postures will make the patient to have different blood pressure value. Most importantly, data was taken when the patient was cycling. During cycling, signals are significantly distorted and corrupted. The patient was required to increase his riding speed at first, then decrease his riding speed later. Blood pressure is expected to increase at first, then decrease after a few minutes. Here is one of the final outcomes. The red curve is PWV, which is calculated by the algorithms from cycling data to estimate blood pressure. Blue curve is systolic blood pressure measured by final press, which is a non-wearable, heavy medical device. As we can see in the graph, they correlated pretty well. They both increase and decrease at similar times, indicating the algorithm works during cycling. Now, let's go into the technical aspects of this project. Firstly, we are going to talk about the theoretical background of blood pressure non-invasive measurements. Then, there are more details about how to make it work. If we look at this graph, the blue curve here is the ECG signal, and the red curve here is not the PPG signal, but the gradient of PPG signal. The time difference between these two peaks is called post-transit time. Post-wave velocity, PWV, is inversely proportional to PTT, and the blood pressure is proportional to PWV. By measuring post-transit time, we can estimate blood pressure. By now, it seems all very easy, but something wrong could happen during motion. This data was taken when the patient was cycling. As we can see in the graph, the ECG signal is significantly distorted. So this is called ECG R wave, and this is called T wave. R wave is usually much larger than T wave. However, in this case, as the signal was distorted, T-wave is much larger. If the peak detection method is using threshold, then this method would fail, and we cannot detect the peak correctly. So a new method must be developed. To solve this problem, let's firstly have a look at ECG characteristics. So this is the ECG frequency spectrum. ECG R peak is usually have frequencies from 5 to 15 Hz, and ECG T wave usually has frequency below 5 Hz. To solve this problem, firstly, bandpass filter is applied so that the cutoff frequency of the bandpass filter is 5 Hz and 15 Hz. So the T wave will be significantly reduced. The second step is to take the derivative of the ECG signal. It is important to notice that the ECG R peak has a much larger magnitude of derivative. Therefore, when we square the derivative, we are really emphasizing the ECG R peak. Then after we integrate back, ECG R peak will have a much larger magnitude. As we can see in this graph, after using the previous methods, the algorithm actually finds the ECG R peak, even though the T wave is larger. However, the algorithm is not actually finding the peak. It is actually one data point left or right. Then we apply a local search to find the maximum point around a local region. Then, in the end, we find the ECG peak with very good accuracy. Now, let's have a look at PPG maximum slope detection. So the algorithm firstly finds the ECG peak, and by using this peak, the algorithm is able to divide all the PPG gradient data into different groups. In this example, there's 1, 2, 3, 4 groups, and for each group, a maximum point can be found. So the maximum point is the PPG maximum slope. However, PPG gradient can be very noisy because any local fluctuation of the original PPG signal can cause a large noise in the gradient. Therefore, we must apply a low-pass filter to the original signal. Here is the PPG frequency domain. As we can see in the graph, a low-pass filter can have a cutoff frequency of 6 Hz. So at this graph, we can see that the PPG gradient is now much smoother with the original signal has been filtered. Now let's have a look at a practical problem that occurred during data collection. The data was collecting when the patient stands up from sitting posture at about this time, and we can see that the ECG sensor was moving violently, so that this package of data was completely unusable. If we use that data, the PTT value does not make sense and have a huge outlier, which will later cause significant inaccuracy in blood pressure estimation. To solve this problem, the algorithm firstly finds the variance of the overall signal, then divide the signal into different windows. And for each window, we find the variance, then compare this variance with the overall variance. If this variance is significantly larger than the average variance, then we discard this package of data. So after this algorithm has been applied, we can see that there's no PTT value estimated because the algorithm has automatically detected the corruption in the data and disregards this package. So here is the overall block diagram of the algorithm. Firstly, the algorithm collects ECG and a PPG signal for 5 seconds, then it compares the signal variance with the reference variance. If the variance is too large, then the algorithm thinks that these are outliers, and these data will be disregarded. Then it will come back to collect more data. If the signal variance is not too large, then the algorithm will apply low-pass filter to PPG and calculate its gradient. Then here, the ECG peak detection method we talked about before is applied to ECG signal, and ECG R peaks are found. After R peaks are found, then the algorithm use R peaks to find PPG maximum slope, which is the gradient peaks. Then use the time difference between these two peaks to calculate post-transit time. If there are 5 seconds of data, then there are typically 5 PTT value calculated. Then the algorithm picked the median of these 5 values because the algorithm has to be outlier resistant. If we find the mean of these PTT values, then the outlier can significantly change the mean. Here we're going to run a simulation of the algorithm. After the data of ECG and PPG are loaded, the algorithm can run without any parameter tuning. It will plot a graph of PWV and SBP, and a regression. As you can see in the PWV graph, there is some points missing because the algorithm suspects that these points are outlier. If you are unsure about one point, for example this point, that you suspect this point is an outlier, you can go back to another program and check. So at this program, it shows all the peak detection and PTT value in real time. So in this case, you can see that, for example, this point, is this an outlier? No, it is not an outlier. Although these points have very high PTT values, it is not an outlier. The ECG peak detection and the PPG maximum slope detection is accurate. Now it is the end of my demonstration. In the future, we would like to firstly collect more data to make the algorithm more rigorous. Secondly, we want to research how often calibration is needed to estimate the blood pressure accurately. Thirdly, we want to use template-based method to improve the algorithm. In the end, we would like to use the algorithm to estimate DBP. Thank you for watching.